Okay, welcome back again to this course in ABE153, and right now we are going to do a sample problem for the keyway, for the design of keyway. And just recall that when we say design of keyway, we are our goal is to specify the length required so that it can resist, or it can withstand the shear forces or the bearing forces. Okay, and just take note, when I say bearing forces, I don't mean the roller bearings, but rather the bearing forces in terms of strength of materials. Okay, so that compressive stress or compressive forces. So that's what I mean by the bearings, bearing stress. Okay, so our problem for this design of QA is taken from the textbook by Fairs, design of machine elements, Fairs, and here it is. That's the example 10.3. It says here, the cast iron pulley is to be keyed to a 2 1/2 inch shaft made of 1040, and it is to transmit 100 HP at 200 RPM. A flat key of cold finish C1020 is to be used. By the way, you would notice here that the shaft key has this material designation 1020, and the shaft is 1040. And recall that in our lesson regarding engineering materials, this 1040 has a greater or has a higher amount of carbon content, which means it is stronger than the shaft key. And that's also the reason why in a shaft assembly wherein there's a shaft, there's a hub, and there's a shaft key, the weakest link should be the key. Okay, so that's just simply because that if we design, it's something, if the shaft key is the weakest, then somehow it acts like a fuse, so it's a protection device. But if the gear fails, then it is or if the shaft fails, then that's gonna be catastrophic. So that's why we just want to have this failure at the key, because it is replaceable. Okay, and let's continue. The drive is expected to be subjected to quite minor vibrations, so that a design factor of 1.75 appears reasonable, and therefore specify a suitable key length. So use Sy is equal to 66 ksi, and recall that the shear yield strength is related to the yield strength in tension, which is equal to 0.5. And this relationship, I think this is from the maximum shear stress theory for ductile materials. And there is another theory coming from the maximum distortion energy theory, and the relationship of the shear yield strength to the yield strength in tension is I think 0.57. So right here, we are just going to use the 0.5 Sy. Okay, so let's continue. For the solution, then the first step that we'll do is to illustrate the problem. Okay, so what it means is, if here's our shaft, right? So here's our shaft, and the diameter of the shaft is 2.5 inches, right? So recall from our relation that this is, the key would be dO over 4. So what it means is if this is d all over 4, that's just 2.5 divided by 4. Therefore, our height is equal to 0.625 inches. And since this is a square key, then the width b is just the same as the height, 0.625 inches. Okay, and the distance from this point to this point, that's just 1/8. So this is 1/8 of 2.5. So this is 0.3125 inches. Okay, so that's the depth of the groove or the kiwi. Okay, and recall that our working equation is just simply L is 2T is equal to 2 times the torque divided by the shear yield strength times BD times the factor of safety. Right, so here's for shear, and for bearing stress, this is L is equal to 4T SYC times the height times the diameter. Here's the diameter of the shaft times the factor of safety. Okay, so let's try to derive this if you can. So if here's our shaft, right, and here's our center. Now for shearing, this will be our shearing area, so right here, right? So that means that the key can be sheared off this way, right? So that means that the shearing area is this one, right? Shearing area. Therefore, if that's the shearing area, then there's going to be a force, a shear force, and the shear force will be located here. So here's our shear force, and let's just label it as F. And since from the shaft you can already obtain a torque, so we have a torque here, and we know that that the force is related to torque through some moment arms. So right here, the moment arm, if this is the diameter, then half of the diameter, that's the radius, or this is right, d all over 2. Okay, so that's gonna be the relationship for the or the expression for the force. Now let's just go back to the stress, which is simply the force all over area, right? So here's the basic equation for stress, is simply the force all over area, and therefore what is the force? So the force is as we have said, that the torque is just equal to force times the radius, or d all over 2. So therefore force is equal to T all over d all over 2, or simply write 2T all over d. Okay, and for the area, if here's our key, and let's say here's our height, and here's our width, and here's our length, right? So half of it, that's where the force will be acting. So what is this area? So the area right here is just simply the width b times the length, right? So width times the length. So here's our area and here's our force. So if we substitute that, we'll get 2T all over d in the numerator divided by the area, b times L, and here the stresses will be the allowable stress. Allowable stress, which is equal to the, of course, if this is shear, if this is shear stress, then it will be shear yield strength right here divided by the factor of safety. Okay, so if we rearrange this, the shear as y, or let's just express in terms of L. So this is 2t all over d times b times sy times the factor of safety, right? So here's the expression. Now let's check. Okay, so it's just the same. So that's for the shear. And for the bearing stress, then actually for the bearing stress, the area will be this area, right? So that means that this is the area, which is just simply h all over 2. So this is h all over 2 times L. Okay, and the force, supposedly the force should be somewhere below, but for simplicity sake, it's just taken at this level. Okay, so if that's the case, then again, for the basic stress equation, the stress is equal to force all over area, but the force is still the same. It's just 2t all over d. Right, this is for bearing stress. The area is h all over 2 times the length. So we get 4t. Okay, 4t all over hl times d. Okay, and here's our stress, and since we want the compressive strength, then this is just S yield strength in compression. And just take note that for ductile materials, the yield strength in tension is just approximately equal to the yield strength in compression. And of course, that's for ductile materials. And if we have a material that's brittle, then we have a difference in the yield strength in compression and yield strength in tension. Okay, so here it is, and in terms of length, then this is going to be 4t over h times d times right, times, okay, we forgot something right here, so there should be a factor of safety, so SYC times the factor of safety. So that's the derivation of the equations. Okay, so now let's apply this in our problem. Okay, so number 2, solve for torque. And for the torque, we use this equation, P is equal to 2 pi nt, and T therefore is just equal to P all over 2 pi n. Okay, and if we substitute the value, what we get here is 100 HP all over 2 pi times, what is this, n, 200 revolution per minute. So we need to convert this HP into foot-pounds or pound-inch, right? 100 HP times 33,000 foot-pound per, or I think pound-foot per minute. Okay, and if we want a value of inch, then of course we need to convert this foot right here. I need to multiply that by 12 inch per foot, so you'll get a value of 31.5 inch kips. Okay, so inch kips is just kilo in pounds. Okay, so that's the torque, and therefore the length for shear is L is equal to 2 times the torque, 31.5 inch kips. What else? Times the shear yield strength is 0.5 times 66 ksi, so 66 KSI times the width of 0.625 times the diameter of 2.5, right, times the factor of safety of 1.75. So 2 times 31.5, right, divided by 0.5 times 66 times 0.625 times 2.5. So this is times 1.75 times the factor of safety, that's 2.14, right, 2.14 inches. Okay, so the next step is to solve for, right, solve for length based on bearing stress. Right, so L is equal to 40 times S, the yield strength in compression, times the height times D times the factor of safety. Right, so 4 times 31.5 inch cubes divided by 66 KSI. What is this? 0.625 inches times 2.5 inches, right, times 1.75. So 4 times 31.5 divided by 66 times 0.625 times 2.5, right, times 1.75, and this is just the same, 2.14 inches. Okay, so let's check the maximum length allowable. So what that means is L max is equal to 1.5 D, and 1.5 times 2.5 inches, so we have 3.75 inches. That means that we will only need, right, so for the summary, you will only need a key that is that has I think 0.625 by 0.625 inches, right, by 2.14, or maybe you'll use 2 1/4, so 2.25 inches. And of course you will only need a single key. And so here's our 2.25, and here's our cross section. Okay, so that's all for this shaft key, and in the next video we'll be discussing shaft couplings.